Now let us look at question 4. A function is defined as g of x equal x by sine x over 2. Obtain the Maclaurin series expansion for g up to determine x to the power 4. So we know Maclaurin is just Taylor series evaluated, where evaluate at 0. So if g of x, formula here would be most said f of 0. G of 0, remember the context is g, so g of 0 plus x times g prime 0 plus x squared g, second derivative evaluated at 0 over 2 factorial plus x cubed, evaluate the third derivative at 0 over 3 factorial plus x to the power 4, evaluate the fourth derivative at 0 over 4 factorial. So we know g of x is equal to x sine x over 2, or sine half x. Alright, so remember x is 1x. So g of 0, I mean if x is 0, then 0 times whatever is 0. So that's straightforward. Alright, so g of 0, so let's do g prime, that's the first derivative. So we use a product rule, differentiate x, we get 1 times sine x over 2. Plus, we'll keep the x now, differentiate sine x over 2, we'll get half cos x over 2, and then we substitute 0. So g prime 0 would be equal to sine 0, and then the other term 0, half 0 times cos, so that would be 0 again. Let's find out the second derivative. So second derivative now. So differentiate sine x over 2, that's half cos x over 2, and now differentiate the next term now with the product rule. So split the half x and the cos. So differentiate half x, we get half, and keep the cos x over 2. Plus, and then now we're going to alternate. So we're going to keep the half x now. And differentiate cos x over 2. We'll get minus a half sine x over 2. And then we evaluate at 0. So this would be g, second derivative evaluated at 0. So this would be half cos x over 2. Now cos 0 is 1, so that's half. Plus half again. And the other term will be 0. So this will be 1. We're going to need that one later. Let's put all we evaluate. Let me just take all we evaluate. Alright. Now I also need the third derivative. Now to get the third derivative, I need to fix up the second. Let me rewrite the second derivative. So half cos x over 2 and half cos x over 2. That's 1 cos x over 2. Just grouping terms that are alike there. And then this is half x times minus half. So that's minus a quarter x sine x over 2. So let's find the third derivative. So differentiate cos x. Differentiate cos x. That will be minus a half sine x over 2 minus, now we're going to treat the quarter x and the sine x over 2 as a product. So differentiate quarter x, I end up with, so let's separate it like that, alright. Differentiate quarter x, I end up with a quarter, and then sine x over 2. Plus, and then now I'm alternating. So this time I'm keeping the quarter x and differentiate sine x over 2. I'll get half cos x over 2. So if I evaluate at 0, then well, everything will become 0, because sine 0 is 0, sine 0 is 0 here, if x is 0, everything will be 0. Now I need to group now, because to get I'm going to need that, to get the fourth derivative, I need to fix up the third. Let me fix up the third derivative. Let me simplify the third derivative by grouping the terms which are alike. Fix up the third derivative. I have minus half sine x over 2, and I distribute this negative sign. I would have minus a quarter sine x over 2. So minus half minus a quarter, that's minus 3/4 sine x over 2. And then the other term, distribute the minus, I'll get minus, and then that's a quarter times half, that's minus 1/8 x cos x over 2. And now I'll differentiate this now to get the fourth derivative. So the fourth derivative, alright, so differentiate minus 3/4 sine x over 2, I'll get, well, half times 3/4, that's minus 3/8 cos x over 2 minus, and then I apply the product rule to this. So differentiate 1/8 x, I get 1/8 times cos x over 2 plus, I'm going to keep the 1/8 x now and differentiate cos x over 2. I'll get minus a half sine x over 2. And then I evaluate at 0. So g, fourth derivative, evaluated at 0. So I'll get cos 0 is 1, so that's negative 3/8. And if I distribute the minus, cos 0 is 1, so distribute the minus at the same time, so that's minus 1/8. And then everything else in the bracket, let's bracket this, and then everything else will be 0. So this will become minus 3/8 minus 1/8, that's minus a half. So which means now the Maclaurin expansion for g of x will be, let's look at what we have here. Let's look at the x formula again. So g of 0, that came to 0, so that would be 0. G of 0 is 0. G prime 0 was also 0, so that term will go on. The second derivative was 1. Second derivative at 0 was 1, so this will be x squared times 1 over 2. So x squared times 1 over 2, which is x squared over 2. And again, let's see, the third derivative was 0, and then the fourth derivative at 0, so x to the power of 4 over 4 factorial times g4 0, which was half. So x to the power of, so minus, this would be half, x to the power of 4 over 4 factorial, right? And the 4 factorial is what? 24. So if we simplify this will be x squared over 2 minus, now 4 factorial is 24. 2 times 24, that's 48. So that was minus x4 over 48. That's the Maclaurin expansion for the function g. Let's continue. Hence estimate g of 2. So let me just rewrite what g of x was. G of x was equal to x squared over 2 minus x to the power of 4 over 48. So g of 2 will be 2 squared, which is 4 over 2, minus 2 to the power of 4, which is 16 over 48. So that will become 4 divided by 2, minus a third. That's 1 2/3. Next, part B, a series is given as 2 plus 3/4 plus 4/9 plus 5/16. Express the n partial sum of the series using sigma notation. So this one is straightforward. If you notice, we don't put 2/1. If you notice, partial sum would be n equal to 1 from 1 to, and they would have no in the final term. So 1 to infinity. And notice, let me change it from k equal, let me change right like this. This will be from k equal to 1 to k equal to n. Notice in the denominator, we're getting squares, so we call that k square, so 1 square, 2 square, 3 square, and so on. And in the numerator, we're adding 1 each time. So for successive terms, so it's k plus 1 over k squared. Let's continue. Hence, calculate the sum of the first 20 terms minus the sum of the first 18 terms. So the sum of the first 20 terms minus the sum of the first 18 terms. Let's remind ourselves what the partial sum was. Sn, sum of k equal 1 to k equal to n. And it was what? K plus 1 over k plus 1 over k squared. No, so if you think about it, the sum of the first 20 terms minus the sum of the first 18 terms. So if you have 20 terms, just subtract 18 terms, you're left with just the 19th and the 20th term. So the 19th term would be 19 plus 1 over 19 square. And the 20th term will be 20 plus 1 over 20 square. And that will be equal to, let's put it as it is in the calculator. And I end up with 0.108. Continuing. Given that the series there, sum of n equal 1 to infinity for 1 over n squared converges, show that the partial sum s diverges. So I'm going to use, if you look at the series here, look at the series here. Notice the series is always positive. The series is always positive because whatever the n value is, just square it, 1 over square, you're going to get a positive value. And the series is also decreasing. If you notice, as n increases for successive terms, the denominator will get larger, so the terms are decreasing. And of course, the terms will definitely be continuous because n is not 0, n starts from 1, so the terms will always be continuous. So we're going to use the integral test. Use the integral test. Alright, so we're going to integrate 1 over n squared between 1 and infinity dn with respect to n. Let's integrate that. So, of course, this we can rewrite this as integral 1 to infinity n to the minus 2 dn, and we're integrating. So we add 1 to the power, add 1 to the power, add 1 to the power, we get negative 1, and we divide by the power, which is negative 1, between infinity and 1. And of course, this is what negative, if I use indices to rewrite this is what negative 1 over n evaluated between infinity and 1. So this will be negative 1 over infinity minus negative 1 over 1. So negative 1 over infinity, there are limits there, so that would approach 0. So this will approach 0. So we're left with the positive 1, so therefore the series actually converges. So therefore the series, since we have a finite value, the series actually converges. So I think there's an error here. Saying the series diverges, it actually converges. Alright? So S of n converges. Let's move on. Use a proof by induction. Use a method of induction to prove that, and we're proving the series here. So to prove by induction, let us at least list out the first 3 terms. So for the first term, when r is 1, the first term, we're starting from 1, right? The first term would be 0. The second term, we replace the r with 2. So the second term will be 2 times 2 minus 1, which is 2. The third term, replace r with 3. So it's 3 times 2, that's 6, plus that. And the nth term will be n times n minus 1. And the summation, we're told it should be equal to n into n squared minus 1 over 3. Now let's go through the steps of induction. So we're going to show through when n equal to 1. When n equal to 1, what's the first term? What's the first term there? The first term there is 0. And the summation for the first term, replace on the right hand side. So the right hand side gives us a summation. Replace n with the 1. We end up with 0 actually. So therefore, true for n equal to 1. Step 2, let's assume true for n equal to k. So we simply replace all the values here with k, all the n with k. So 0 plus 2 plus 6 plus, and the n term there would be k, the k term, k into k minus 1. That should be equal to, replace n with k into k squared minus 1 over 3. K into k squared minus 1 all over 3. Next, show true for n equal to k plus 1. So next is a show true for n equal to k plus 1. Alright, so we're going to write out the term up to the k plus 1 term. So continuing from step 2, advancing 0 plus 2 plus 6 plus that plus, and now the k term is k into k minus 1 plus, and the term that follows this will be k plus 1 into k, and this should be equal to, replace k with k plus 1, so we have k plus 1 all square into, replace k with k plus 1, so k plus 1 square, k plus 1 square, and this will put this all over 3. So remember, look on the right hand side, it gives us a summation formula. So we are summing k plus 1 terms, so replace the k with k plus 1. Alright, so we ask a question, because we're not sure if left hand side is equal to the right hand side. That's what the proof is all about. Alright, so let's begin with the left hand side. Let us show it's equal to the right hand side. So the left hand side is equal to, now from 0 to k into k minus 1. Likewise, from 0 to k into k minus 1. You recognize that that's equal to, from step 2, 0 to k into k minus 1 is equal to k into k squared minus 1 over 3 plus, and what we have here now, k into k plus 1. We want to show that this is equal to what we have on the right hand side. So we can put this over 3 and multiply numerator by 3, whole IDF equivalent fraction. So we have one common denominator of 3. So this is 3. And by the way, there was no k square here. Alright, so replace k. So there was no k squared there, just k. So replace k with k plus 1. Replace k with k plus 1, so it becomes k plus square minus 1. Alright, so let's continue. So what can we do now? If you notice, we can rewrite, so this k, we can rewrite k square minus 1 as k plus 1, k minus 1, that's a difference of 2 squares. Plus, and then put the 3 at the front here, so we have 3k, k into k plus 1. And we can factor k plus 1. We factor k plus 1 in the bracket. What we will actually have now is k times k minus 1, which is k square minus k. In the second factorial k plus 1, we'll actually have here now, if we factor k plus 1, we'll actually have 3k. So this will now become k plus 1 into k square minus k plus 3k, that's 2k, all over 3. Continuing, we can complete the square for the second bracket, so we have k plus 1, and let's complete the square. This would be k plus 1 all square. Half of 2 is 1, and then minus 1 all over 3. And notice, this is what the right hand side is. Notice what the right hand side is. K plus 1 into k plus 1 all square minus 1. That's what we're trying to prove. So this is equal to the right hand side. So therefore, true for n equal to k plus 1. Hence, true for all n, where n belongs to the set of natural numbers. Let's continue. So now we are at question 5. In how many ways, how many numbers made up of 5 digits can be made from the digits 1 to 9 if each number contains exactly one even digit and no digit is repeated? So no digit is repeated. So if we have 5, so 1, 2, 3, 4, 5, so 5 distinct objects, and the number of ways to choose 5 distinct objects. So 5 distinct numbers in this case. The number of permutations will be 5 factorial, which is 5 times 4 times 3 times 2 times 1. What's that? 120 ways to choose 5 numbers, but we have some restrictions now. The restrictions are one of the exactly 1 must be even. Now if you think about it, we have 4 even numbers. What are the even numbers? The even numbers are 2, 4, 6, 8. So we have 4 even numbers, and number of ways of selecting any one of these would be 4, choose 1, which is 4, and we have 4 even numbers, and what now? We have 5 odd numbers, which would be 1, 3, 5, 7, 9. So 5 odd numbers, and we're going to, and from the 5 odd numbers, we're choosing 4. So that's 5 choose 4. So the answer to the question, so the solution for this question, in terms of what we're asked, the number of ways of selecting 5 digits. So it's 5 distinct numbers, so it's 120, and the 120, 5 choose 4. 5 choose 4 because 4 of them have to be, so 5 choose 4, because we're selecting 4 odd number from 5, and we're selecting 1 even number from 4 even numbers. So we have 5 odd numbers, 4 even numbers. So from the 5 odd numbers, we're selecting 4 of them, and from the 4 even numbers, we're selecting 1 of them. So 120, let's put in the calculator, 120 times 5 choose 4. What's 5 choose 4? 5 choose 4 is 5. 4 choose 1 is 4. So 120 times 20, that's 2,400 ways. Part 2, determine the probability that the number formed in part A1 is less than 30 grand. Now, for the number to be less than 30,000, the number will have to begin with either 1 or 2. Because 5-digit number for the number, so for the number to be less than 30, the number has to start with either 1 or 2. So let's look at the case where if the number begins with 1, then the number of permutations we could have is actually, so remember, if number begins at 1, so remember 1, if number begins with 1, so we'll have space now for 4 other odd numbers. Remember, it's 5 odd numbers that are supposed to be in the number, so we'll have space for 4 odd numbers, which can be arranged in 4 factorial ways, and 4 factorial, and remember we'll have 4 even numbers, so times 4 again. Since if the leading number is 1, you'll be left with 4 odd numbers and 4 even. So 4 numbers, that's 4 factorial, and then times 4 odd numbers and 4 even numbers. That will give us 120 ways. If the number begins with 2, then the number of ways. So if the number begins with 2, what will happen now is that you'll have space now for 3 even numbers and 5 odd numbers. Sorry, 4 odd numbers and 3 even numbers. Actually, that came out wrong. So we'll already have the 1 even number that's allotted. So remember, each number from A1 should have only 1 even numbers. So the rest will be just, so from the 5 numbers, the rest will be 4. The rest of digits will have to be odd. And remember, we have 5 odd numbers, and we're picking 4 from those because they are already even. So this is even, and we have 1, 2, 3, 4 slots, and we're picking these 4 numbers from the 5 odd numbers that we have there. So that would be 384. So the probability, so we add these two values, 120 plus 384, over the total that we have in A. Well, the total was 2,400. So divide by 2,400. So we should end up with a probability of 0.2. Next. A and B are two matrices given as that. Determine the value of x for which the inverse of A does not exist. And the inverse of A does not exist when the determinant is 0. So we're going to let the determinant be equal to 0. So we're going to let the determinant of A be equal to 0. So let's find the determinant of A. And I'll be using the cofactor method. So the inverse of A, so we're going to take 2 into 0 minus 2 minus x, and the cofactor x would be 0 minus 4, and we're going to take minus 1, the cofactor minus 1 will be 3 minus 0. We're equating all of that to 0, so here we'll have minus 4. 2 times minus 2, that's minus 4. Minus x times minus 4, that's positive 4x. And then that's minus 3 equal to 0. Solve. We end up with 4x equal to 7. Divide both sides by 4. X equal to 7 over 4. Or 1 3/4 or 1.75. Part B, given that the determinant of AB is equal to minus 10, show that x equal to negative b. Show that x equal to 2. So before we can find the determinant of AB, we first need to find AB. Let's find AB. Actually, no. We don't. So determinant, we don't need to find AB. Determinant of AB, we are told is equal to minus 10. And there's a rule that says determinant of AB is equal to determinant of A times the determinant of B. So determinant of AB is determinant of A times the determinant of B, and we'll put that to minus 10. Now let's remind ourselves what A was. Determinant of A, here we have it here on the left hand side, determinant of A. We found it to be 4x minus 7. And B, let's look at the determinant of, well, determinant of B, we're going to have to find that. So determinant of A is 4x minus 7. And let's find the determinant of B. I'm going to use a cofactor method to find the determinant of B. Determinant of B, let me just do it right here. Determinant of B, I take the 1, so 1 times the cofactor of 1, which is 2, 3, 6, so 6, which is 6 minus 4, that's 2. The cofactor of minus 2, that would be 4 minus 8, that's minus 4. And the cofactor of the 5, that's 2 minus 6, which is minus 4. So if I do all of this calculation, the determinant of B would be 2 plus 8, that's 10. 10 minus 20, that's negative 10. So come down here. So determinant of A would be having 4x minus 7. And the determinant of B we found to be minus 10. And we're told that's equal to minus 10. So we can divide both sides by minus 10. So that into that, so we have 4x minus 7 equal to 1. Add 7 to both sides. We end up with 4x equal to 8. Divide both sides by 4. X is equal to 2, as we're asked to show. Let's continue. Hence obtain A inverse. So A inverse is 1 over the determinant of A times the adjoint of A. Now the determinant of A we had found to be 4x minus 7. Remember x was 2, so that will be 4 times 2, 8 minus 7 equal to 1. So the determinant of A was 1. So let's find the adjoint of A. The adjoint of A is equal to the matrix of cofactors. Matrix, the transpose of the matrix of cofactors. The transpose of the matrix of cofactors. Let me write that proper. Alright, so let's get the matrix. Now we need to look at what A was. Let's remind ourselves of what the matrix A was. So A, now I put A beside here. So A, remind ourselves what A was. A was, there is A, and remind ourselves that, remember the X value is 2. So just copy that down there. Let's restate it. Alright, so A was, so we have 2, 3, 2, 2, 0, 1, minus 1, 2, 0. So we're going to replace each element with its cofactor matrix, with its cofactor, alright? So we're going to replace 2 with its cofactor. That's 0 minus 1 times 2. Right, that's minus 2. Replace 2 with its cofactor. That's minus 4. And we change the sign. Replace negative 1 with its cofactor. That's 3 minus 0. That's 3. Replacing 3 with its cofactor. That's 0 plus 1. And we change the sign. Minus 1, replace 0 with its cofactor, that's 0 plus 2. Replace this 2 with its cofactor, that's 2 minus 4, that's minus 2, and we change the sign, right? So when we're following this, we change the sign, so plus, minus, plus, minus, plus, minus, plus, minus, plus. Right, so we at the final row. So replace 2 with its cofactor. That's 4 minus 0. So it's just 4. Replace 1 with its cofactor. That's 4 plus 3. That's 7. We change the sign to minus 7. Replace 0 with its cofactor. That's 0 minus 6. We'll keep that. Alright. So good. So that's the adjoint of A. Now the inverse is 1 over the determinant times the adjoint. Now the determinant is 1. So the A inverse is just. So A inverse then is just, we just take the transpose. So the rows become column. So this becomes minus 2, 4, 3. Minus 1, 2, 2. 4. Minus 7, minus 6. So that's the inverse of A. Part C. In an experiment, individuals were asked to select from 2 available colors, green and blue. The individual selected 1 color, 2 colors, or no color. 70% of the individuals selected at least 1 color, and 6,000 individuals selected no color. Given that 40% of the individuals selected green and 50% selected blue, calculate the probability that an individual selected both colors. So we have blue and green, right? We draw a Venn diagram there to represent all of that confusing thing that was set up there. Alright, so it's a universal. So we have green and blue, right? Blue and green. So we have blue and we have green. Let's go through this now. So 40% of the selected green and 50% selected blue. Let me go from top again. 70% selected at least one color. So that means 30% no select none. Alright, 30% would be outside here. 30% selected neither. Alright. So let's call this X. So that's the one who selected both. So 70%, 40% selected green. So 40% selected green. And 50% selected blue. So this is 50 minus X. So this is 50. This will be 40 minus X. For 50% minus X. Let me just leave a percentage. So we just assume it's percentage. I need space. Let me just delete the percentage. So we know it's percentage. So 50 minus X and green. So 40 minus X and 30% was neither. So to solve this, to get the amount for both, right? So we can add up. So 50 minus X plus 40 minus X plus 30 equal to 100. So minus X, that's cancel. 0. So we get so we have here now. So we have 40, 50 and 40 and 30. That's what, 120 minus X equal to 100, which means that rearranging that X would be equal to 20. So 20 selected both. So the probability of both would be, what we have an intersection there, X, 20%. Next, determine the total number of individuals who participated in the experiment. If we go back up to the top of the question, we are told that 600 persons selected no color, which would be 30% here. So 30% of the persons selected no color. So 30% of the total equals 600. Alright. So let the total be n. So 0.3, and I'm going to call the total n equal to 600. So I divide both sides by 0.3. So n equal to 600 divided by 0.3, and that will give me 2,000 persons. Next. So we are on to the final question on the paper, question 6. Question 6. A differential equation is given as dy by dx, x dy by dx plus y equal 2 sine x. Show that the general solution of the equation is, and we're given something there. So we're going to use the integrating factor method. So we're going to divide each term here by x. So we're going to get dy by dx plus y over x equal to 2 sine x over x. So we divide each term by x. So let's find the integrating factor. So the integrating factor is equal to e to the integral of the coefficient of the y, which is integral of 1 over x dx, which is equal to e integrate 1 over x, we get log x, and e to the log x is equal to x. So we're going to multiply each term here by x. Alright, so x times the integrating factor is x, so x times dy by dx, that's dy by dx. X times y over x, that's y. And x times 2 sine x over x, that's 2 sine x. So we have the integrating factor. So now we can integrate both sides with respect to x. So the left hand side is the integrating factor, which is x, integrating factor, which is x, times y. Integrate 2 sine x, we get 2 cos x. Integrate 2 sine x is actually minus 2 cos x plus c, and in the transpose for y, we can divide each term by x. So if we divide each term by x, we end up with y equal to minus 2 cos x over x plus c over x. And you recognize that it's the same thing we have here. It's just that now we put the c term at the front and the cos x term after. So we just rewrite it like this. So c over x minus 2 cos x over x. Let's continue. Hence, determine the particular solution of the differential equation that satisfies the condition y equal to 2 when x is equal to pi. Let's just rewrite the equation. So the equation was y equal to c over x minus 2 cos x over x. We're going to substitute now 2 for the y and pi for the x. So c over pi minus 2 cos pi over pi. And of course we can times both sides by pi. So we end up with 2 pi equal c minus 2 cos pi. So equal 2 pi equal to c minus now cos pi. The value of cos pi is minus 1. So this becomes 2 pi equal c plus 2. Therefore c would be 2 pi minus 2. Which means that the particular solution is just rewriting the equation and replacing the c value. So the particular solution is y equal to c, and c, we just found c to be 2 pi minus 2. 2 pi minus 2. So it's over x minus 2 cos x over x. Part, and they give us what we should get. Alright, so first we can factor, it's obviously a separable differential equation, so we can factor what y in the numerator here. So factor out y, we're left with x minus 1 over x squared minus 4, and then we can multiply both sides by dx over y, times both sides by dx over y. We times the left hand side by dx over y, we'll end up with dy over y. Let me call it 1 dy over y. And if we times the right hand side by dx over y, we'll end up with x minus 1 over x squared minus 4 dx. And of course now we can integrate both sides. So integrate the left hand side, we'll get log y equal to the right hand side. Can we integrate by recognition? No. So I think we'll have to rewrite it. Let us use partial fractions to rewrite it. Let me just separate it over here. So I'm going to let x minus 1 over x squared minus 4 equal to, now the difference of squares here, so this will be a over x minus 2 plus b over x plus 2. These will be the factors. So x minus 1 over x squared minus 4 will be equal to a into x plus 2 times x squared minus 4. If I multiply numerator and denominator by x plus 2, the same I can multiply numerator and denominator by x plus 2 here. So I'll get b into x minus 2 over x squared minus 4. So we can just let x minus 1 be equal to a into x plus 2. So we can drop all the denominators since they are all the same. Plus b into x minus 2. So we can let x be equal to 1. If x is equal to 1, we'll have 0. If x is equal to 2, this bracket will cancel. So we end up with 4a. So a is a quarter. So we can let x be equal to minus 2. So that will end up with minus 3. So minus 2 minus 1 equal to, this will become 0. And we'll actually have minus 4b. So divide both sides by minus 4. B would be equal to 3/4. So rewriting this on the right hand side there, expression on the right hand side there, we'll end up with a over x minus 2. What's a? A is a quarter. So 1 over 4 x minus 2. Right? Plus b. B is 3/4. So 3/4. And we have x plus 2, 4x plus 2 there. Alright. So let us integrate now. So we have ln y. Integrate the right hand side. We'll have a quarter log x minus 2 plus 3/4 log x plus 2 plus a constant k plus k. And we can call k plus k. And we're using plus k instead of plus c. Since the question, if you look at what we're asked to prove, they use k here to be the constant here. So instead of c, we just use k. Alright? Let's continue. Alright, so continuing. So we have end up with ln y. And then we know one of the laws are indices. The laws are logarithm. The quarter we can put here. So we can ln x minus 2 for a quarter there, plus ln x plus 2 the power 3/4 there. Actually the constant, let me call the constant c. And then I'm going to call this now ln k conveniently, where c equal log k. So continuing, so we can combine all the logs. So we have ln, we're going to combine all the logs now. So we have x minus 2 to the power quarter times x plus 2 power 3/4. So combine all the logs times k. Alright, so we'll log everything there in the square bracket. And now we have, remember if log A equal log B, so we can drop the logs. It means A equal B, so we can drop the logs and say that y is equal to log y is equal to what now? So everything to a quarter. So we can actually it's x minus 2 to the quarter, right? So same fourth root. So this fourth root. And then this is x minus 2 times x plus 2 cube times k. And the k, we can put the k at the front here. Alright, so it's exactly what we're asked to prove in the question. Right, exactly what we're asked to prove. Let's continue. Solve the equation. Alright, so homogeneous second order differential equation. So we can call equation here. So we can let m square minus 2m minus 2 is equal to 0. And of course, this is easily factorized. Can it be factorized though? Actually, this is minus 1m. That's minus 1m, so factorize easily. So m minus 2, m plus 1. So for the solution for the auxiliary equation, m equal to 2 or m equal to minus 1. So the roots are real and distinct. So y equal a e to the 2x plus b e to the minus 1x. Now we are told that when x equal minus 1, y equal to 1. And when x equal to 1, y is equal to 0. So we're also going to get a pair simultaneous there. So let's substitute x equal minus 1, y equal 1 first. And then after, on the other side, we're going to substitute x equal 1, y equal 0. Alright, let's do that. So x equal minus 1, y, so y is 1. So a times e to the minus 2x plus b times e to the x. In the other equation, x equal 1, y equal 0, so y equal to 0. X equal 1, so we get a e to the y. Why do I have to put the 2x here? If x is minus 1, so that will be minus 2. And if x is minus 1, positive 1. Right? If x is y 0, if x is 1, so a e to the 2 plus b e x is 1, so that's minus 1. So we have a pair simultaneous equation here. Right, so this one looks easier to transpose. So from here we can say that be to the minus 1 equal a e square. Divide both sides by e to the minus 1. That's that. So b is equal to a e cube, and we can substitute it in this. Right, so we're going to replace b with a e cube, so it's a e to the minus 2. We're going to replace b with AE cube times E again. So 1 is equal to AE to the minus 2 plus AE to the power of 4. If we do some factoring, so 1 equal to A into E minus 2 plus E to the 4. Divide both sides by the bracket. So 1 over E minus 2 plus E to the power of 4 is equal to A. Now to get rid of the negative power, we can times numerator and denominator by E square. Let me just do that. So times that by E square times denominator by E square. So we end up with E square over E to the 0, which is 1, plus E to the power of 6. And the correction, this should be minus. So it should be minus. So it should be minus. Let's put it there. So it should be all of these should be minus, because B equal to minus AE to the cube. So divide by should be minus, and then it should be minus equal to A. And now to get the B, now we can substitute it. So therefore now B is equal to minus A. So minus this times E cube. So minus E cube times A, which is E square over 1 minus E to the power of 6, which is equal to minus E to the power of 5 over 1 minus E to the power of 6. Alright, so let's write in the solution now. So remember the equation was, the general solution was y equal to AE to the 2x plus BE to the minus x, and my value for A is equal to this, E square. So it's E square over 1 minus E to the 6 times E to the 2x plus B, and B, what's B? Well, should it be minus? So I put actually, so minus E to the 5 over 1 minus E to the 6 times E to the minus x. That's the end of the paper.